Hey everybody, welcome back. Kestava here with another problem today, and have some exciting updates for you. As you can see, I've now gone digital, so I'll be working with a smart board here, or smart tablet. Yeah, so I'm excited for these new changes and hopefully improvements. So, I'm excited. You're probably not too excited. People do this all the time, but I'm excited. It's my first one today. If it doesn't go so, swimmingly, give me some feedback in the comments of stuff that I could do better next time. Without ado, our problem today is a design of a steel beam with a penetration in it. So this comes up extremely frequently in the professional engineering world, where you design a beam or a column or pretty much anything you design, the contractor comes back while the building or structure is under construction and they say, hey, we need to notch out a piece of this beam, we need to make a hole here, we need to make a penetration here, or this actually comes up a lot when subcontractors come in and they put in their duct work or their pipes for heating and cooling. So your HVAC, your plumbing, electrical needs to run lines. So all of that needs to jive together. So a lot of the time, we can't just have perfect beams everywhere. There's usually penetrations all over the place. So if a contractor asks you to make a hole in something like a beam, how do we know if it's still structurally adequate to withstand the loading that we have? So we're going to jump right into that. Let's go. So today we're working with a W10 by 12, and I will be using the steel construction manual, so the AISC steel manual, the 14th edition, the maroon red one, as I have been in my previous videos. So throughout this, I'll be referencing tables, and if there's some weird table that I want to go into, then I will also take a snapshot of that page as well. Today we have my favorite, and again, this beam scenario, I know I do it a lot, but it's just a simply supported beam with a distributed load across it, which we will denote as W. Span length is 10 feet, and it's braced every 2 feet. Our loading criteria is we have a dead load of 400 pounds per lineal foot, and we have a live load of 800 pounds per lineal foot. Design under LRFD criteria, and our governing load case is going to be 1.2 dead load plus 1.6 live load. So obviously that gets us 1.2 times 400 plus 1.6 times 800, which comes out to uniform load of 1.76 kip per lineal foot. So this is actually divided by 1,000. And that equals W. Okay. So next we need to try to find, or not try to find, but we're going to find the maximum moment in shear, which is denoted as MU and VU. Well, let's start with VU. VU, we know from our design tables in table 3-23. For those who are a little bit newer to this, this is a little more advanced of a problem, but you can still definitely follow along. VU for simply supported and with a uniform distributed load on it is the equation WL over 2. So we have all of those components, 1.76 KLF, remember kips per lineal foot, times 10 feet over 2. That's 8.8 kips. And we know from our shear diagram that we're going to denote this as A, and this side is B. So A, and we have B. We know our shear diagram like that, with our max at the ends. And at midspan, we have 0. Okay? Mu, we know the equation, WL squared over 8. Come on, that one's like classic. But we have 1.76 KLF times 10 feet squared over 8, which equals 22 kip feet. And we know that that one is A, B. This is our moment diagram. And our moment diagram is going to look something like that. And we have 0 moment at the ends, and we have our maximum moment at the midspan. So L over 2, L over 2. Okay. I know, first grade stuff, right? We're way past that. Totally advanced now. Contractors asking us to make holes in the steel, so come on, way by this stuff. But it's always good to refresh yourself to make sure that you really remember all the steps here. So we have now found our max moment and shear. That's denoted by these here. That's good. Now we need to find the moment and shear capacities. So I'm going to stop a second. So what I'm doing here is just confirming that the size of the steel that we have is adequate, and then we're going to make the penetration, and then we're going to figure out what our reduction capacity is, and if it's still adequate to resist the loading criteria that we have. So that's what I will be doing today. So really quick here, we're going to find phi mn and phi vn. And we know that phi vn equals phi times 0.6 area of the web Fy CV. Well, we know that the area of the web is the thickness of the web times d of your member. Thickness of the web excuse me, lid, is, if you go to table 1-1 in your steel design manual, that's at the very front. It gives you all the properties. And we have if we go back to the top, a W10 by 12. And so we have thickness of the web is 0.19 inches. And our D is 9.87 inches. So area of the web is those multiplied together, which equals 1.875 inches squared. And that's because for shear, the web is the only member that's transferring shear through your member. It's kind of, yeah. So if we, if I kind of dash it out over here, the portion of steel that you get to calculate that transfers shear is actually that right there. So you can take all advantage of all of that. And so that's what we've done here. So that's that outline there. That is your AW. Okay. We know that phi typically for shear is 0.9 unless we prove otherwise. And then our Fy, our grade of steel, is 50 KSI. As we do know that all W sections, typically, unless they're very custom, are grade A992 steel, which equals 50 KSI, grade 50. Okay, so we know that. So we still have this CV value, right? So if we go into the back of our steel manual and we go to chapter G and we go to G.2 because we have a symmetric member. So members with unstiffened or stiffened webs, that's what we have with our W section. You can go to part 1 for shear strength, and it says on page 16-68 for webs of rolled eye-shaped members, which we have, with H over thickness web, less than or equal to 2.24 square root E over Fy, CV equals 1.0, and V equals 1.0. So let's see if we have that. So you'll go back to your properties table, and so table 1-1 at the beginning, and you will find out that your H over thickness of web is equal to 46.6, and that's just tabulated in the table for a W10 by 12 section, for all sections. So that's always stated. And so is that less than 2.24 square root E over Fy? Let's remember E for steel is 29 times 10 to the 6th psi. And then we have Fy above. So to make Fy and E units match, we need to, and we have a square root here. So you want to bring everything into psi. That's a good rule of thumb there. 50 will now become 50,000 psi. You'll have 50,000 for Fy. And then E, it's just as we said. Okay. And that'll get us, once calced out, is less than 53.9. So that is true. So that's okay. So that means that V equals 1.0 and CV equals 1.0. Okay, awesome. We have everything to solve for phi Vn, which equals now, so phi is now 1.0, 0.6. That's just a factor in there. That doesn't get changed. It's part of the equation. AW is 1.875 inches squared. Fy is 50 ksi. And CV is 1.0. And that equals 56.3 kips, which you know is greater than VU, which equals 8.8 kips. So, okay, plenty of capacity. We're good there. And if you don't want to go through all of that, save yourself some time. You can also, if I can spell, also find this value in the Z table, which is table 3-2 in the steel manual. It gives you this value for, again, for look up the section that you're using, so W10 by 12, and it actually gives you this phi Vn value right away. So yeah, that's assuming though that that CV equals 1.0. So you just need to make sure and run this check just to make sure everything's good to go. But yeah, that's a real easy way to check our moment. VMN. We can go to table 3-10. That's our available moment versus unbraced length. So we'll go through that chart, and we have a W10 by 12, and we know that it's braced every 2 feet. That's denoted over here. And we just need to find our W10 by 12, which is really small, so it's going to be towards the back. It's going to be actually the last page, so page 3-134. W10 by 12 for 2 feet is 47 kip feet, which is greater than mu, which equals 22 kip feet. Okay, we're good. And lastly, now we want to find max deflection. So for a uniformly distributed load on a simply supported beam, again, in our shear and moment charts, in table 3-23, your max deflection for that criteria, or for that loading condition, is at midspan, and it's equal to 5 WL to the 4th over 384 EI. Okay, so we're finding the deflection right now of the non-penetrated shape, so we can just get our I value, which is our section modulus, so IX. That is from table 1-1. Again, that's in the properties section, so that's already found for you which is 53.8 inches to the fourth. W, we know, is 1.76 kips per foot, but little catch here, this is LRFD factored. When we're finding deflection, we can use unfactored loads. So what that actually equates to is just the 400 PLF dead plus 800 PLF live, so live load, dead load, which equals 1.2 kip per lineal foot. And so that's what we have there, so that's nice. We have an L of 10 feet, which we want to break down into inches, which equals 120 inches. And actually KLF we want to break down into kips per inch, which equals 0.1 KLI. Deflection, you always want to make sure all of your variables have the same, or all of your units match one another. So E is steel, 29 times 10 to the 6th psi. We are going to use, since we have KLI, we can use KSI. So this actually becomes, if you divide by 1,000, 29,000 KSI. And then that's everything. So we'll plug all that in. That gets us 0.17 inches. And the contract, let's see, we have a tolerance. I didn't really give it, but let's say we have a tolerance for this problem of a quarter inch. So we can't be deflecting more than a quarter inch for this beam. So less than 0.25 inches. Okay. So we're going to have to keep track of this and make sure that we don't cross that plane and that we also have enough strength in our beam once we make this penetration. So now, contractor wants to make a 6-inch diameter, 6-inch diameter penetration at midspan of beam at center of beam. So what I'm talking here is we have this. That's our beam. And that's our top flange. Our bottom flange. Simply supported. And what we have, contractor wants to make that penetration 6 inches deep. And that'll be located in the center of the beam. So EQ, that just means equals equals. So both those dimensions have to equal each other, which means that the center of the circle penetration is located within the center of our beam. And if we look through a cross section, that would look like this. So that's what we have to deal with now. So let's figure out if that's acceptable and we can let that contractor do that or not. So now we need to find the new moment and shear capacities. Phi VNs, something kind of cool here. So if we remember back up top with our shear diagram, this is why we try to draw all this out because we can back reference it. Something that's cool is that your shear at midspan is 0. We know this already. So and we know that all shear transfers through the web of the element, and cutting through the web of the element, there's no shear transfer at that location. So in reality, we can just ignore having to recheck the capacity of the member at that location, because although it's a reduction in shear capacity, so although phi VN, we're going to call it effective, so once it's cut, is less than phi VN original, we are comparing it to a VU, which is, 0 at the center line, And then you'd say, well, 3 inches each direction because the penetration is 6 inches wide. You're even at that 3 inches, your VU is still relatively 0. So no matter what you reduce your VN effective to, you're comparing it to 0, which means that you will have enough capacity at that location. So, rule of thumb, if the contractor wanted to put his penetration, on the ends, that's when we'd worry much more about our shear capacity, and actually we'd then subsequently worry a lot less about our moment capacity, because down below here, our moment capacity is actually I should say our ultimate moment is greatest at the center line of the beam at midspan. So that's where we're going to take the biggest hit. So we need to definitely check our moment. But then if the contractor wanted to make a penetration at the end of the beam, although shear would be a concern for us, our moment wouldn't be a concern for us because it's almost 0 at the ends. So something to think about when someone asks you, hey, we need to put a penetration somewhere along this beam. Could you give us guidelines as to where we can do that? And that's what you want to keep in the back of your head is, well, at the ends, you have to worry more about shear transfer. But at closer to midspan, you have to worry more about your bending moment and less about your shear. So, okay, moving on. That was a little rant there. Sorry about that. So, okay, by inspection. But now we need to find phi-mn. And phi-mn, we need our new elastic section. That's our zx. First, you want to solve for your elastic section. So my equals sx fy. We know that sx equals ix over c. And our new section, so all of these z's and s's and i's that we had tabulated before in the steel manual, well, now we have a brand new section that's sliced up. So we can't just take those values anymore, so we need to calculate them ourselves, which sucks. So although we have a penetration, it's located directly in the center of our beam. So we know that our section, our cross-section, is still symmetric about the y-axis, or the neutral axis, I should say. So we still know that that distance equals that distance. So that's nice. It makes it a little easier. But what we're going to want to do is we need to find our effective I. We're going to call this 3, which means you need to break it down into sections. So you need to do your summation of Ix, and that's going to get us into I1, I1 plus A1 D1, or yeah, D1 squared plus I2 plus A2 D2 squared. So I already know that I don't want to do that. And I know that when you're learning in school, they make you go through that and figure all of that out, and it drags everything on. But this is the professional world. Time is money. So we have a little trick that I'm going to share with you guys. So instead of doing all of that, we can do something like this instead. So we know, check this out. We know that the original Zx equals 12.6 inches cubed. And that you can find from your table 1-1 in your steel manual under the W10 by 12 section. So that's the unpenetrated section. So all we have to do is figure out what our new Z, the Z of the section that we're removing is. And so what I mean by that is, what is this section right there? So that's kind of nice because now that's only a nice geometry. So it's 6 inches tall because it's a 6-inch penetration, and it goes through the web of the member, so thickness of the web. And we know, since our section is plastic, we know that Z equals BD squared over 4. So we're going to go with this. B, which is just the same thing as thickness of web here, that's base width. Thickness of web is 0.19 inches times D, which is 6 inches squared over, see, I'm already making mistakes here, over 4, which equals 1.71 inches cubed. So that is the section modulus, the plastic section modulus of the section that was lost. So the part that they took out. So if we want to know now Z effective is going to equal Z original minus, we'll call it Z prime. So that is just 12.6 inches for original minus 1.71, which gets you 10.89 inches cubed. Now we know phi mn effective. Everything, once the penetration is made, everything is going to be called effective. Equals phi fy, because we're using LRFD, times Z effective. That's going to bring us to 0.9, 50 KSI, and 10.89 inches cubed. We're going to divide that by 12 to get it at a kip inch into kip feet, and that's going to equal 40.8 kip feet, which is greater than MU, which equals 22 kip feet. Boom! We are okay in terms of bending. So for strength in terms of bending and strength in terms of shear, we're okay on both accounts. The last thing we have to do is figure out, are we okay with deflection? So find new max deflection. And same thing, we know equals 5, the equation, 384 EI. But now we need I effective. Okay, so just like needing to find a new S, we need to find a new I. So, come on. Let's do summation of I, which equals going to be I1 plus A1 D squared plus I2. Whoa, wait a minute. We're not doing that again. We're going to do the same trick as before. So we're just need to find I, we'll call I prime, of the section that was lost. Come on, got to make this simple. Time is money like we were talking about. So we know that's 6-inch penetration, and again, thickness of web. I prime equals base times depth cubed over 12. That is going to be 0.19 inches. D is going to be 6 inches cubed all over 12, which equals 3.42 inches to the 4th. So I effective is going to equal I original minus I prime. I original is 53.8 inches to the 4th. This is in table 1-1 in the steel manual. It's already calced out for a W10 by 12, so don't go calculating that yourself. You can just pull it right out of the manual. And then I prime is 3.42 inches to the 4th. So not a big reduction, and I'll talk about that in a second here. So I effective is going to equal 50.4 inches to the 4th. So now, if we run our max equation, plug everything in like you did for the first part, all the way back up when we originally found deflection. That is now going to get you 0.185 inches, which is still less than our 1/4 inch allowable deflection. So we are okay on all accounts. So we good. We can tell that contractor, go ahead and make that penetration. Just make sure it's centered in the beam and it's at the center point, at the midspan of the beam. Otherwise, we're gonna have to run calculations again. So you really want to be strict with telling them the guidelines on where they're able to put that. You don't want to just give them free rein and say, yep, a 6-inch penetration can go anywhere, because it does affect the beam differently depending on where it is. What you can see here, what you can pull away from some of this, is that taking out portions of the web at the midpoint of your section. So if I scroll back up to here, so because we took it out of the center here, the reduction in your moduli, both your Z, your S, your I, didn't reduce by a whole lot. So you still had those values pretty much intact, which then directly correlate with the strength of your member. So as you move further away from your neutral axis, so if you start to clip off, say you clipped off that portion of the flange, or they took off the whole, God forbid, they took off the whole bottom flange, that's when a lot of things start going wrong, and that's because you're taking away a component that is far from your neutral axis, which what that does is the way that it counteracts, so you have moment happening about this section, and the way that that moment is, I guess how do I want to put this? The way that the moment is counteracted is through a force couple, and the force couple happens from a depth of that, and then you have two forces, top and bottom, which is your top and bottom flanges, and that's where it's resisted in terms of bending moment, that is. So that all correlates within the equations to your neutral axis and how far away it is. So if you start destroying or removing bits that are far away from neutral axis, it's going to make big impacts. But as a rule of thumb, if you keep it tight to the neutral axis, the effects are usually minimal. Not always, but that's usually what it correlates to. So, and as you can see through our equations, because although we took out a 6-inch portion of our web, that really didn't reduce our effective I or our effective Z at all, really. I mean, a fun little thing to do is if you did Z effective over Z original, 12.6, that's still going to be 86% capacity. So it's a 14% reduction in terms of Z, and then your I, it's even less. So that one is 93% capacity. 93. So it's a 7% reduction in your geometry. So really not a lot of change there. But yeah, that is it for today's example. So tell me what you think. I know it was a little clunky here, moving around, kind of got sporadic at some points, but I really like this. I think I'll be able to get a lot more information across a lot more clearly. Please like and subscribe as always. I really do enjoy doing this stuff. I'm looking forward to more and more days of being able to make more and more videos for you guys. I mean, ultimately, it's for all of you. So, I enjoy doing it. And if someone's struggling, if there's one person out there that's really struggling, and they need a voice that can calmly or very clearly explain something out to them. I really hope that I can be that voice that helps out. So yeah, until next time, this is Kestava. I'll see you guys later. Bye.